Good morning, everyone, to the third day of the workshop. Our first speaker today is Professor Bishakhdatta Gayen, who's a joint faculty at the Indian Institute of Science and the University of Melbourne. So please.
Thank you. Hi. Thanks for everyone here. So I think last 2 days, you guys are listening about ocean and particularly talking about ocean circulation at the same time, like a linear or more like, geostrophic regime. Okay. So I like to switch gear. So I like to go for more like a non-linear aspect of the oceanography. Okay. And how are we going to deal with? Okay. I know it is a big challenging, whereas the ocean has a large scale is so big and the small scale is down to the millimeter or centimeter. Okay. So let's start with that. And why we are interested about ocean? Okay. Of course, because of those ocean circulations. When you say circulation, don't get confused by circulation means like a big scale. Circulation means motion. Okay. Motion in any scale is called circulations. Okay. So now why so important? Of course, we know this thing. Heat and mass transport regulate CO2. And particularly when you talk about the heat, ocean uptakes much more heat compared to like a heat storage is a capacitance. Okay. And then also regulate CO2, marine biology, water cycle. And in the long term is dictate the climate and weather. Now, if we want to understand the ocean, we need to understand the source, like any system, any physical system, it has a source and sink. Ocean has a similar things. It has also have a source, and then I'll come back to the sink. So in the source, we usually divide into two parts. One is the buoyancy forcing, another is called as a mechanical forcing. Okay. So when it comes to the buoyancy forcing, it means is temperature and salt flux or freshwater flux. Now come to the mechanical forcing, you have wind, because wind is blowing over the ocean surface, and the tide. And that tide is associated with the moon or sun. So two types of tides we have. Now, for a moment, just assume it is a balanced system. Okay. I know ocean is constantly evolving and evolving in a short time scale and also evolving in a decadal time scale or sentinel time scale. Okay. But for a moment, it is a quasi steady state. Okay. So if you think about that, then there should be energy is losing and we get kind of a equilibrated state, like a quasi steady state, not absolutely steady state, because it's impossible. This system is dynamically evolving system. Now, when you look at this, the main, what is called sink of energy. So these sinks of energies I listed here. These are not the full list, but these are the kind of like a dominant list of the small scales, where you have a bottom drag, bottom turbulence. You can see this is the ocean, then this is your bathymetry of the ocean. And you see the ocean was very rough. Okay. It also has a sea mount and everything. So this will constantly give you a drag. Okay. Same when you're driving a car, right? So always there is a drag there. Okay. And that decide how fast you can move, but it is not a driver. Okay. I'll come to that point. Now, you have the internal waves, because ocean is, most of the ocean is stably stratified. And in the first day, when Jim was mentioned about this internal wave, so I'm not going to go to the internal waves here. So what is I'm trying to talk about here, like this is another way energy go to the small scale. Then another very important small scale in the ocean is called small scale convection, which will be I'm mainly going to talk about in this next two lectures. Then near surface turbulence. Okay. You see there's a wind there. So many activities going on at the top of the ocean. So it's the most active part of the ocean. Like top 100 meter is the most active. Okay. Dynamically very, very energetic ocean. And there you get a lot of turbulence. Okay. And that's why you create a mixed layer. Okay. So stably stratified system where density is a function of, say for function of depth. Correct? And you mixing up here. Once you're mixing up here, it evolves to a stage is like this. Okay, this part and this part is because of the conservation of mass, and it makes a mixed layer. If I take the what is called derivative of this profile, say for this is the density. If you take a derivative of this profile, it will look like okay. I'll come to that point, but what is I'm trying to tell you about, you get a mixed layer because of this lot of turbulence in the upper ocean. Now, also there's a called loss of balance. I'll talk to this point. So, what is the meaning of loss of balance? We always talk about geostrophic balance. Okay, because of the rotation and because of the Coriolis and pressure gradient balance. It's same like in atmospheric large scale flows. Ocean has the same, is a balance, but not every time you get this perfect balance. Many occasion, many time and many spaces, this balance get disturbed and you get agiostrophic motion. And that is another way you get the small scale motion. Now, again, this is the bottom drag, bottom turbulence, also the interaction with the bottom boundary. So because of this big mountain, when the tidal flow is lossing over it, it also feel form stress. This is we talk about the form stress. Okay. There is another kind of cascade is happening. It's called geostrophic turbulence. It's like a two-dimensional turbulence. That again leads to a inverse cascade. Okay. But we are main interested about this forward cascade, because if you have a real sink, then this equilibrium can be established. Now, probably you have seen this one. I'm not going to go details. Just to show you, there is a wind there over the ocean. And this wind is also having a different pattern at different latitude and longitude. Okay. So you have a easterlies, westerlies, and very interesting properties in the Southern Ocean, because if you look at the Northern Hemisphere, Southern Ocean, a big contrast. All our lands are mainly in the Northern Hemisphere. Southern Hemisphere is very less land, except the Antarctica, and then there is a big band of ocean, okay, where the wind can blow enormously, and that is called the highest westerlies in there. Now, when you talk about the buoyancy forcing, these are the one is driving the buoyancy forcing, and this SST and SSS manifestation from the heat flux and salt flux. Okay, if you look at the pattern of the SST, this is the annual average pattern. The SST is relatively high at the equator. As you go further north and south, it is very cold. SSS is very interesting pattern. It is, we call as a bimodal structure. It is always high at the mid latitude, okay, and at the equator, because of this what is called ascent of the Hadley cell, the ICTZ is there, you get lot of rainfall. Similarly, rainfall also happen in the polar area, okay, and there rainfall usually transfer into the snowfall, okay. So here you lot of get snowfall. So in same way, you get fresh water to the system near the equator, and these two locations, like a mid latitude, you get lot of evaporation. Okay, so it's take all the moisture and then uplift around the equator. Okay, combine this thing, you get SSD, sea surface density. Okay, very interesting. The SST and SSD is follow the similar pattern, but that is like the present state of our system. Okay, and we know this ocean is constantly evolving because of we are getting more towards the salinity or freshwater driven system. Okay, I'll come to that point, but for now the sea surface density is more like a follow by temperature. So temperature is actually at presently still dictate the sea surface density. Now, if you look at the vertical section or zonally average view of ocean, it is usually has a one cell or two cell depending on which ocean basins we are talking about. Okay, so here we are talking about two ocean basin. We are talking about mainly Atlantic Ocean basin, where this is a schematic of two cell structure. Okay, one is cell, it is called upper cell, another is called lower cell. I know you have seen this thing. Why I'm trying to show you here, if you look at these cells are there, these cells are also experience upper ocean mixing as well as bottom ocean mixing. We talk about the again small scales. So these small scales are playing an important role, the manifestation or modification of this large scale ocean circulation. This is the similar view here. What is I'm showing it here? Showing is the buoyancy forcing, mainly the heat. Typically, you get heating around the equator and cooling at the pole. And technically speaking, the highest wind state over the Southern Ocean. Okay, so these are, and then if you go back to the other part of the ocean, still has the wind force is higher, but this is where is the wind force is significantly higher. So you can see here, these are the way ocean get forcing from a mechanical source. Okay, I didn't talk about the tide here. So another way ocean get force from the tide. Okay, that was called is a M2 tide or solar tide or K2 tide or everything. Okay, now I'll quickly go through the overturning circulations. So here, this overturning circulation is not like, just confined in one plane. It is a very three-dimensional in nature. And you can see here, this is a different overturning circulation at different ocean basin. And they get intermingled between one basin to another basin. And that is the way the water must exchange, okay, property got exchanged between one ocean basin to another ocean basin. And this exchange is, so mixing means like the small scale process is playing a very important role of this inter-basin exchange, or even inside the basin, you can see that small scale processes in the upper ocean and the bottom of the ocean is also playing a very important role of modifying this cell. This was a cartoon, is like quite popular. So what is he trying to show you here? It is Antarctica and the connected, and this is the Southern Ocean around the Antarctica, and they connect the three main ocean basin. So this was the Pacific, this is your Atlantic, and this is the Indian Ocean sector. You can see here, because of you have this Southern Ocean, most of the water is come to the Southern Ocean and get churned, and then again come back to the respective ocean basin. So it's a quite interesting and quite complex system. Now, when you talk about this ocean circulation, we usually divide the ocean circulation or large scale ocean circulation into two parts. One is the surface intensified system, another is the overturning system. So surface intensified system, when you talk about, we talked about gyre and boundary currents. Every ocean except Indian Ocean has two prominent gyre we call subtropical gyre. There is also have a subpolar gyre, but subtropical gyre is the more prominent and more energetic gyres are there. Okay, and each gyre is associated with the western intensified current. When I'm showing is intensified current, I just show you the prominent is the Gulf Stream, Croatia, and then is Agulhas current. Okay, and this, whatever the picture you are showing it here, this is, we cannot be expressed in terms of a geostrophic balance, because you see there is a lot of going on in this current. Okay, there is a forming small scale eddies, forming the mesoscale eddies, submesoscale. I'll come back to the point, but I'm showing it is a very, very dynamic and very unsteady process. Okay, now largest and most speeding current around the Antarctica. Okay, you can see here, and it full of with again eddies, filament, fronts, everything. So you can expect that ocean is full of eddies, or you can think about in a fluid mechanics sense we call as a turbulence. Okay. Now, why we really care about the small scale and why do we really care about the ocean circulations? Yes, today we are facing a problem of climate change, and it has been reporting quite last a couple of decades. This ocean circulation is changing, okay, and now last 10 years it's changing rapidly, okay. So we really need to care about this ocean circulation and the connection of the small scale with the ocean circulation. While come back to the point with the small scale before is saying, so what is actually people are reporting? People are saying the big currents, big overturning circulation, one is, I told you, North Atlantic overturning circulation sail, Antarctic bottom water sail. This is a very recent paper. They first time reporting the lower sails are slowing down. They have been talking about this upper sail is slowing down. And now also people are start to saying there is a slowing down of specific currents also, okay. So this is the big concern, because these currents distribute the heat, because you are only heating in the equator, and this heat has to be distributed to the pole. If you can't distribute the heat to the pole, what will happen? Pole get colder and equator get warmer, okay. Yeah, so that's fine, but if you get cooler, you feel like, oh, so maybe in the future you get so cold, you'll get back to all the ice covered in Antarctica. Yeah, that was called natural cycle, okay. But we are now experiencing much faster, okay. So we might have to go to the deglaciation stage much faster, and then response is quicker. So we'll go much faster seashore response. And still with a lot of doubt it's there, will we go back to the stage in our past deglaciation stage or not? Because present system and the past system is quite different. So there is a lot of debate is going on. What is the stage we are heading for in future? Now, even in the IPCC, they reported it is rapidly slowing down, and probably they also expecting in 100 and 200 years, the overturning circulation is going to collapse, okay. That is a very big disaster if it's a collapse. Now there is a very loose connection about this, what is called slowing down. One of the connection people are started to making it, when is the overturning is slowing down, they're also finding the convection in the ocean is also decreasing, okay. And when you talk about the convection, in oceanography, they usually talk about convection in the pole, okay. I'll come to that point. So what is they reporting there? The convection in the pole is decreasing, which is actually from the dense water, okay. I'll come that point, okay. But for now, there is also reports going on that this convection around the pole is rapidly dropping, okay. So, and when you talk about convection, is the first thing you understand is a small scale, okay. So there is a very loose connection of the small scales with the overturning circulation. Now, with all these slides, what is the challenge so far? The challenge is we still not clearly know the role of small scale to the large scale overturning circulation. So small scales is really matters, because they are the sink of the big system, okay. If you have a bigger sink, then the motion is also small. So it's vice versa. So you really need to know this small scale, and the connection is important. Now, we also don't know this how rapidly this ice is melting in the ocean. And you probably have listening all this in the news, right? The ice caps are every now and then one iceberg is disappearing, one iceberg size of New York City is just cabbling up, okay. So there is also rapid interaction between ice ocean, okay. The small scale is playing a very important role of melting those ice, okay. And that place is so remote, we cannot quantify it properly, okay. And that also changes the sea surface salinity of the ocean, because when the ice is melt, it adds the fresh water. The same way is the rain, correct? You see the evaporation and rain, ice has a very similar like a mechanism. When ice is formed, it reject salt, same like evaporation, okay. When ice is melt, it added the fresh water. similar like your rainfall. Okay, so our hydrology cycle is changing. At the same time, is the ice-ocean interaction is evolving, and that, how much time we have it? 30 minutes, right? Okay, good. Yeah. So that was also very big challenge. So you can see that small scale is also playing a role of understanding how fast this ice is melting. Now, why I'm stressing too much here? Because these small scale processes are not well represented in the large climate and ocean models. Okay, so they are very crudely parameterized. Okay, and if they quickly parameterize, then our prediction can be wrong. How fast the sea level will rise or how fast the system will change, that is the way we have to plan, right? Adaptability, everything. Okay, so it is very important for us. Now, to come to the point, I haven't said that they are important. Why we can't do it? Just because of this huge range of scale. You are all listening from the day one. And I'm just trying to summarize which model so far can address all the scale. Okay, back again, you see that overturning circulation, which is scale of 10,000 kilometers from pole to pole distance. And then go back to the turbulent convection, which is in the scale of millimeter to centimeter. Okay, in between, you have this, little bit relatively small circulation called Southern Ocean. And then this is a very interesting boundary we call as a mesoscale. Mesoscale means still the geostrophic balance is very much holds. Okay, and that scales is one of the dominating scale, or lot of energy is sitting in that scale. Okay, when you look at the ocean, you always feel like, oh, they're typically this AD size. Okay, and of course, I think you probably heard about this Rossby deformation scale. Okay, I think heard about Rossby deformation scale, right? Can you raise a hand? Good. Okay, so the Rossby deformation scale is dictate this size of the mesoscale ADs, and this Rossby deformation scale is also depends on the rotation, earth rotation. So more you go to the pole, the Rossby deformation area is smaller. So when you look at the satellite picture of the ADs, you always see these ADs are very big in the equator, and as you go further, they're very small in size. Okay. Now, that is the where you start to break the geostrophy. This is something like 100 kilometers. After this 100 kilometers, things are very, very different. The vertical components are become very important. Okay, so before that is a geostrophic, is more like a horizontal type of motion. Okay, after that, the system get coupled. So horizontal, vertical is coupling each other. Okay, so energy is no more confined in a horizontal plane. It go back to the vertical plane and then come back. Okay, so both motion is get strongly coupled, and through this strongly coupled, it also undergoes much faster motion. Okay, and leads to this very, very small scale, and finally they good dissipation. Now, it's very interesting scale in the ocean is called submesoscale. Submesoscale means like the scale smaller than the mesoscale. Then we comes internal waves, surface waves, and turbulence. Interestingly, the large scale ocean models only able to get little bit about the mesoscale. So we are started to call AD, we don't call AD resolving. We start to get some energy from the mesoscale ADs. So if you look at this ocean models in 10 years back, it's completely different. You don't see much ADs there, but now you can see a lot of ADs because now they start to capturing these mesoscale ADs. Of course, then if you really want to understand this small scale, lower than the mesoscale, okay, then you have to use the ROMS, okay, regional ocean modeling system, okay, that able to capture down to 1 meter, because they are so expensive to run it because of the resolution, both the time and spatial, okay. So you're not able to go down further to the small scales of turbulence. So they have also limitation. So they also use a parameterization, okay. Now in the modern century, we start using CFD lot in oceanography, okay, and we feel like that is the only way one can bridge the gap from here to here, okay. So ocean model is approaching from here and try to go down. So let's say if we use some very high resolution model without parameterization or very minimum parameterization, then we can faithfully calculate or faithfully resolve the small scale, and then send some information to this big model. So both way is called complementary approach, okay. So one of the very famous, probably you all know, it is used in the extensively in the fluid mechanics community as well as in engineering community, is called direct numerical simulation, okay. When you say direct numerical simulation, it's like you already heard about Navier-Stokes equation, right? So they just discretize the Navier-Stokes equation without making any assumption and solve it. And you can understand, if I don't make any assumption, that means I have to solve the smallest scale of the motion, okay. And Kannaviran was talking about the smallest scale of the motion. Anybody? Smallest scale of the motion? What is this called? Exactly, Kolmogorov scale. Anybody else? Even smaller than the Kolmogorov scale? Bachelor scale. Okay, which bachelor scale is smaller? Temperature or salinity? Any guess? Temperature? Salinity, correct? So salinity bachelor scale, okay, is, you know how much, how small it is depending, it is also depending on the temperature also, okay. So it is smaller, is 100 times smaller, roughly 100 times smaller than the Kolmogorov scale, okay. So that scale you have to resolve it. So that means that scale is down to the even fraction of the millimeter, okay. So DNS means you have to resolve it, because that's why you call it the DNS, okay. So that means the DNS cannot resolve the big scale, because if you resolve the small scale, we have same resources, right, for the ocean model and for the DNS. So if you have same resources, either you have to resolve only small range of scale, which is Jim was talk about range of scale. So range of scales is very important concept for the modern century, okay. So how big span you can resolve it, okay. So 10 to the power 3, 10 to the power 4 is just right now we touching 10 to the power 4. So, and this whole scale is 10 to the power 6 to 10 to the power 7 order of scale, okay. So it's impossible in next even 100 years, we can, any model can resolve all the scale, okay, it's impossible. So there should be a complementary approach. Now, one of the complementary approach is called large eddy simulation, okay. It's very interesting, and it is actually have also parameterization, but that parameterization is also energetically conserved, okay. And with the large eddy simulation, you are not claiming to resolve the small scale of motion, okay. You are resolving some part of the small scale, but at the same time you can start to resolving the big scale, okay. Now how big? Again back to the range of scale, okay, because that is your limitation, okay. You cannot claim you are resolving everything, okay. So back again 10 to the power 3 or 10 to the power 4 you can resolve it. So depending which scale I'm targeting to resolve at the small scale, okay. So if I targeting to resolve, say for what is called in the meter, then I can go up to 10 or 100 kilometer, okay. And this particular is big challenge for ocean, okay, because ocean has a big range of scale, okay. For atmosphere is the challenge is much lesser, okay, but ocean is challenge is significantly because we have a big range of scale. Even the small scale and the large scale is operate huge range. In atmosphere is not like that. Even small scale and large scale and intermediate scale, sometimes they operate in a very same range of scale. Okay, so it's much more easier. So for ocean circulation, predictability is a big challenge in the modern century, and we have to what is called conquer this challenge, because ocean plays a significant role of driving weather and climate because of, again, highest heat capacitance. Now, this was a very, very fancy simulation, was running in a modern supercomputer. So they only can resolve up to 5 kilometer or 10 kilometer. Okay, whatever you see it here, these are all this balance flow we call as a geostrophic flow or mesoscale ADs. Okay, so submesoscale, no. So we are missing big thing here. So those are actually parameterized. Okay, and how good they parameterize is a big question and very important actually to address to understanding this large flow feature. Now, alternative. Okay, when you say call as a complementary approach. So this complementary approach has been used in many ways. One, you know, that laboratory. Okay, we have been using laboratory for running ocean in a tank. Okay, and now with the use of the modern supercomputers, now we start to simulate the same lab setup in computer. Okay, we using called DNS or LES, and there is a very interesting concept called dynamical regime. Okay, when you run a ocean in a tank, that means that tank is behaved like a big ocean, right? It is like a prototype concept. It's like engineering concept, right? So when you're making a spaceship, you make a small prototype so that that prototype will experience the same dynamical forcing. Okay, once this prototype is forcing the same dynamical forcing, then we can run many ensemble simulations. Okay, and understanding the parameters, how the parameter depends on the system, because we cannot afford to run a big system for a multiple time. So we have to go through this process. That is the way we make the spaceship. We cannot make a spaceship several times, right? But we can make prototypes several times. The same concept is also used in this DNS and LES setup. Okay, then from there they get the data. Okay, and then also there is an approach called theoretical approach. Okay, theoretical means started from the Navier-Stokes, simplify it, and get some functional relationship. Okay, when you say functional relationship, simple. Velocity, function of forcing. Okay, I'll come back to all the forcing, but velocity forcing, heat flux for the forcing, and look at the data. How the data is actually giving the theoretical scaling. And once the data and theory both matches, we got very nice scaling. We call it a scaling. Okay, and that scaling we can use for predictability. Not only for predictability, that scaling can plug it back to the large scale ocean model, because they cannot simulate the boundary layer because it's impossible. They have to simulate the big system. So the boundary layer is not there. Okay, so the boundary layer where you see that lot of flux is going on. Okay, say for air-sea boundary layer, ice ocean boundary layer. So all these fluxes, right? When you say fluxes, means a functional relation. Simple as a functional relation. So they need to know this functional relation. If we can able to give this functional relationship to them, then they don't need to resolve it. They just use this functional relationship and move on. Okay, so that's why this plays a very crucial role of giving this functional or theoretical relationship. Okay, now back again, the concept of this direct numerical simulation, LES or lab. Okay, so this has to be dynamical regime. When you talk about the dynamical regime, first thing we have to understand, we cannot talk about in a dimensional sense. So dimensional sense is become irrelevant. It has to be a non-dimensional sense. That is the most important. And in the non-dimensional sense, we need to think about lot of non-dimensional number. And you have last 2 days, you also encounter these numbers, correct? So here I tried to put as much as number possible in there. Maybe there is a more number there, but these are the numbers are more dominating number for controlling the system. Okay. One is the Rayleigh number, Grashof number. So those are like called forcing, the buoyancy forcing, strength of the buoyancy forcing. Ekman number, strength of the rotation forcing. Rossby number is the comparison between the buoyancy forcing and the rotation. Okay. Aspect ratio. This is another very, very important thing in the ocean. Ocean is just a thin sheet of paper. Okay. Aspect ratio of the ocean is 10 to the power -4. So when you look at any ocean data or ocean profile, you actually zoom in and then you look at it. You zoom in like a 10 times, 100 times, and then you're able to see it. Otherwise, your ocean is just thin paper. Okay. So that's another big challenge of resolving this vertical motion. Okay. And also those non-dimensional number, they're significantly high. I don't think we can actually achieve this number in next 50 years in running in DNS and LES. So that means even DNS and LES cannot resolve the all scalars of motion, because once you approach this number, that means you are actually resolving the all scales of motion of the ocean. So these are the number we always have to keep in mind, even you running your ocean model. Okay. So which number I am resolving, even you running a big model, that doesn't mean it is a very, very highly turbulent system. It might be a moderate turbulent system. Okay. Now, so today I mainly focus about the small scale in the upper ocean. Okay. And tomorrow lecture I'll talk about the ice ocean interaction and the connection of the small scale with the large system. Okay. Now switch gear. Upper ocean dynamics is the most energetic and most complex system. Because of the forcing, almost all the forcing is available in our planet is applied at the ocean top surface. Okay. You see here, it doesn't have any space there to put a forcing there. Okay. So everything is forcing, and there is a feedback. Feedback means one forcing is depends on another forcing. Think about very simple way. Okay. If there is no wind, correct? Ocean still evaporates. Like if you keep a glass of water, correct? It will evaporate in 1 month time. But if I put a blowy wind there, it will evaporate faster. Okay. Once it evaporate, what will happen? Ocean surface get cooled. Same like when you sweat. Evaporation nothing was like ocean is sweating, correct? And ocean get cooled. So you see, wind, forcing, the cooling and everything is interconnected. Okay. So there is a very difficult just to look at in one forcing, because all the forcings are absolutely interconnected. And that drives this, the upper layer, mixed layer. Okay. And why is it important? It's the same reason. Because this is the where is the heat get absorbed to the subsurface. And when you talked about the thermohaline circulation, right? So that thermohaline circulation is the big cell is moved through this mixed layer and through the thermocline. Okay. So there is always an exchange of the motion between this large scale and the small scales. Okay. And they having feedback to each other. Okay. Now, before we going to the the smaller scale, I just like to tell about the eddies, which is we call as a geostrophic mesoscale eddies. Okay, two kinds of eddies are in the ocean is very common. One is called cyclonic eddies, okay, anticyclonic, and that depends which hemisphere you are. Okay, it is a cyclonic, is a anti-clockwise in the northern hemisphere. Southern hemisphere is inverse. And this cyclonic eddy is also very interesting vertical structure also, depending which latitude. Okay. But so far, the geostrophy can explain the structure or the balance of these eddies. Okay. And this Rossby number or you always see this equation before last 2 days, right? This is called the geostrophic balance is established in that regime. Again, back to again the non-dimensional number. Okay, you cannot just say, oh, I have this rotation and I have this scale. No, doesn't make any sense. There has to be some force balance. You see the force balance, what is done in here, inertia force divided by the rotational force. When inertia force is much smaller compared to the rotational force, then rotational is playing a big role of what is called making the system horizontal. Okay, in a lot of rotation, that means you're not able to go down, you're just making a circle and circle. Okay, so that's what's called is the geostrophy. Okay, and also you talk about this thermal wind balance, right? So I'm not going to talk about thermal wind balance or like there is a gradient of, so I'll not talk about that. Now, these eddies, even the mesoscale eddies, geostrophic eddies, they not remains as a geostrophic eddies. Very interesting, because these eddies are also get interacted or also get influenced by other forcing. When you say other forcing means another forcing, you have fresh water in the system. So now fresh water will going to deform this eddy structure. So this is the work Nihar did. So he looked at the Bay of Bengal. These are eddies, is geostrophic eddy, but once these eddies is suck fresh water, they get deformed and twist. Okay, so no more we can get a geostrophic assumption after this, because as soon as you get the fresh water, the Rossby number is go to the 1, even larger than the 1. Okay, now this is the time we need to know the loss of balance or agiostrophic flows. Okay, and there's a many agiostrophic motion or many way you can get this agiostrophic motion. So first is, or dominants are written here, is called baroclinic instabilities. Okay, I think you what is called Anand probably going to talk about all these things in his lectures. Okay, so I'm going to touch this. I'm going to mainly touch is this part. Okay, and then you have seen Kelvin-Helmholtz role instability. Okay, it's called shear instability. This is another interesting thing. It's not baroclinic instability, not convective instability. Is called symmetric instability. It's like convection along the sloping surface. Okay, then we have inertia and centrifugal instability. Okay, after agiostrophic motion is get disturbed, then you get all this instability. And apart from that, this is a very another interesting instability always occurs in the ocean. Okay, day and night time, when you have n square itself is a negative. N square means the stratification is reverse. Okay, you see the internal waves, right? When the n square is positive, this is absolutely inverse system. Waves to a wave to a motion which is moves the system away from its equilibrium. Okay, that is called convection. This is a stratified system. You see, these are waves. Now, I'm reverse it, where I am heating at the bottom and cooling at the top. Okay, so that means I am densifying at the top surface and de-densifying in the bottom surface. It's an inverse system, and you know you get this again fast motion. So this will excite immediately fast vertical motion. Okay, that means inertia force is so important here. You're going to hit a Rossby number much greater than 1. And then these are the numbers is playing a very important role called Rayleigh number. Okay, Rayleigh number can be defined based on the temperature between the two surface or can be flux. Okay, so this is the way we define the Rayleigh number. And also very important role is called Prandtl number. Okay, so that means the diffusion of the motion compared to the diffusion of the heat. Okay, so Prandtl number play very important role in the convection. We call it the natural convection here, of course. And then this is also called forced convection. Forced convection means in top of that you have a motion in the flow. Okay, so this is a very idealized concept of convection, or this is one of the things you first learn when you understand the convection. Okay, Rayleigh-Bénard convection. But this ocean is much far away from this idealized system. Okay, and I'll come back to the point now. If you look at this ocean structure, the vertical structure, this is the temperature structure, this is salinity structure, right? You don't compare anything with the Rayleigh-Bénard scenario, right? It is very different. And it has also two scalar system also. Okay, so that makes this convection is very interesting. Okay, we'll come to the immediately after that. Now you have these two systems are playing a role of making the ocean stratified or destratified. When you say destratified means one can be stable, another can be unstable. Okay, but both can give you stratification. Okay, stable stratification. This is one scenario. Another scenario, both can give you a n square negative. So both can drive convection together. Okay, but in ocean, very interesting. Most of the cases, ocean is either one is stratifying it, another is destratifying. So there is always the competition between the two scalar because you have a two scalar. Okay, the same thing is atmosphere. You have a temperature and moisture. Okay, sometimes they also feedback each other, walking in the same direction to contributing to the buoyancy or opposite. So similar as the ocean is, this is two scalar. Now, we can expect two systems to drive a stratification. One is the warm and salty and cold and the fresh, and cold and fresh and warm and salt. This is the two options you have it, okay, to get a stably stratified system. Okay, unstable system is simple: salty and cold, warm and fresh, right? But this is the way you can get stable state system. Okay, and why you get convection in here? Because of the last time I mentioned about the scale of the motion again is very important. Okay, and who decide the scale of the motion? How fast one diffusion, how fast the system can diffuse. Okay, so again the scales of the system is very much important here. The scales of the salt is 100 times smaller than the temperature. So salt is diffused 100 times slower. So if you move a one parcel, okay, to another location, it retained its salinity, but it changed its temperature or heat content much fast. It's very different than atmosphere. In atmosphere is adiabatic process. Okay, so they still remains it. In here, that is expanded, but here they don't expand. The water molecule don't expand. Here, they exchange heat so fast. Okay, and once you move this parcel here, heat is diffused, right? So what will happen? This parcel has high salinity, but less heat content. So it is a denser compared to that area. It continuously sink. Okay, so you get this type of scenario called salt fingering. Is it okay? I'll just take 15 minutes extra. No. From 11:30 I'll finish. It is okay. Okay, perfect. I'll run a little bit faster. Okay. Okay. Now another scenario, the same. I move this parcel here, okay, which is cold, and now heat is coming inside the parcel, correct? So it will get a thermal equilibrium with the heat, but that parcel is still fresh in the surrounding. So what will happen? It will go back. Okay, looks like, oh, this is like internal waves. No, this is not internal waves, because in this whole process is constantly losing its temperature. Okay, so it get very, very different oscillatory motion. Okay, we call as a oscillatory instability, or the name call is a diffusive convection. Okay, so it will go away from its equilibrium, because internal waves is a very different. Okay, it will always come back to the equilibrium, but here it get oscillation, but it is a very fast oscillations. Okay, that leads to again instability. Okay, so this we call as a diffusive convection. Now, avoid that what is called that movie, but I will play this one. This is the DNS, okay, because you have to resolve this small scale of motion. You get these very, very tiny structures. And because of the salt doesn't diffuse, the retained is safe. Okay, the structure still retained is morphology. It's very interesting. Now, other case, the diffusive convection, this experiment is very look like your natural convection, but it is two composite convection. Okay, but structures are very, very same. Now, after saying that, you understand this two different convections, correct? One is just a simple convection. Another is because of your two scalar, you have two types of convection, correct? So now real system, of course, real system is always these two scalars are present, and that's why you expect this type of convection. Can we see those type of system in the presence of other forcing? Because real system as also have other forcing. Okay, so this is from the mooring in the Bay of Bengal, and these are the all forcing. Again, when I talk about the forcing, I talk about wind forcing and freshwater forcing, and this was a Q net. Q net means the in one particular location, how much is the ocean is losing or gaining heat. Okay, ocean can be gain heat many way. One is exactly, and losing it louder. How can ocean lose heat? Yes, evaporation, correct. Another?
Maybe the glacial breathing.
There is another way, but another way is the long wave, the black body radiation, correct? Ocean is losing, okay? We call it. So net long wave, ocean is also losing heat, okay? So short wave, ocean is always gaining heat, okay? So these are the two big components, and the third one is the latent heat, okay? So these are the three total components. You make this ocean either gaining heat or losing heat, okay? This is another interesting, how is the ocean get fresh water or salt, okay? Evaporation minus precipitation. This is I am talking about away from the pole. In the pole is a different story. In the pole is the back again, ice is melting or ice is freezing, okay? So the same concept is like evaporation and precipitation. Now, this is the simple, like, small time scale. One of the smallest time scale we have called diurnal time scale. Okay. In the diurnal time scale, you can see this red one is ocean is gaining heat. Okay. It has to be opposite way the plot should be done, but I didn't make this plot. Okay. It was in the paper. So this is the where ocean is gaining heat. This is during the daytime. And during the night time, ocean is start to losing heat. Okay, and you can see the structure of the mixed layer during the when you lose heat. When you're losing heat, you get a bigger mixed layer. When you're gaining heat, you're shallowing the heat mixed layer. Okay, you can make a big very immediate connection. Oh yes, because I'm losing heat, so I'm driving convection. Okay, so this is the another way you can excite small scale at the night time, okay, by making this small scale, because you are creating an unstable stratification. This is very similar to atmosphere boundary layer also. During the daytime, atmosphere boundary layer get bigger, right? Because you're heating from the below. Same is ocean, you are cooling from the top, okay? Now, similarly, you see the lot of motion and or lot of what is called like a dissipation or mixing is also associated with this diurnal period. Now, so can we able to resolve these scales? Yes, we can do, because this system we can resolve with the help of LES, okay, not DNS, because it's very difficult, because still is the vertical scales are much bigger than what is called than tackled by the DNS. So with the help of LES, we can run this type of system in called is a box model. Okay, in the box model, you usually assume a periodicity in the horizontal direction, and vertical direction you assuming a non-periodic system. Okay, top surface you can put whatever forcing you have it. Bottom, ocean is very large, so you're not able to capture this ocean. Okay, so you use some sponge layer so that you feel like ocean is infinity from the bottom. So this is another tricks we can use it to resolve this upper ocean system. Now, anything else? Yes, and we can actually run two cases. So I have chosen two cases here. Switch on the evaporation and switch off the switch on and switch off the evaporation. Okay, so this problem was done by PhD student Devang. So what equation we solve? Again, we have to solve the entire coupled Navier-Stokes equation. And you see here, when you have a LES, then we need a closure. There is a no LES, this red part is absolutely off. It is the total Navier-Stokes equation without any parameterization. So this is the parameterization we're introducing first time. Okay, and this parameterization is energy conserving when you're using LES. Okay, because still we able to resolve as much as small scale. Okay, so there is many way. I'm not going to deeper of that parameterization, but for now we're using the parameterization and let's run it. Okay, I think we missed the movie, but anyway. So this is your diurnal cycle. Can you see here? This is a heat flux, right? So you are losing heat in the night time and gaining heat at the daytime. Okay, and here I'm showing a vertical RMS. Okay, so that vertical RMS velocity you can see here during the blue is the highest magnitude, correct? So you see here during the night time you get lot of vertical activities. Okay, and more interestingly, when you're looking at n square, you can see these white patches means negative. So you have a negative system during the night time. And also this system I'm putting a wind. Okay, there is always a wind there. You cannot have without wind the system. Okay, so when you have a wind there, they also putting a stress on the ocean surface, and now you have a convection. So what happened during the night time? The entire stress get advected down by the convection. It get trapped in the thermocline. You see, the same stress you applied at the top surface now move down. Okay, it's called what do you call it? Descending of the shear layer. Okay. And this is the called Richardson number criteria. I'm not talking about, but this is the criteria you can use it like when the system go to the shear instability. But this criteria doesn't work well when you have a convection, because Richardson number nothing but shear square divided by n square. When n square itself is negative, we cannot use the criteria. Okay, so this criteria holds when system is stably stratified. Okay. Now, interesting. Now my system is having evaporation. Okay, so that means day and night I'm cooling the ocean surface, correct? Not the cooling the ocean surface, I'm rejecting the salt. Okay, in the daytime I'm warming it from the top surface and rejecting the salt. So what type of instability we expect in the daytime? Salty, warm at the top. Salt fingering, exactly. You see, salt fingering. You get salt fingering. In the night time, both system is unstable, correct? So you get natural convection. Okay, so you see, even in the real system, you can actually see this interesting phenomenon of salt fingering and non-salt fingering. Okay, so this is also showing you the temperature and salinity structure. Okay, so during the night time, you see is homogenized. This is the night time. Okay, during the daytime, it is one is stable, another is unstable. Okay, this is like budget. You don't have to go all this equation. How turbulence is get created? Okay, if its turbulence is created by the shear, it will show up in the called shear production. If turbulence is created by the buoyancy, it called as the buoyancy production. Okay, so you can clearly see during the daytime is a different system and during the night time is a different system, because daytime you still have a stably stratification. Even you have a convection stably stratification, so you drive lot of shear production in the daytime. Okay, in the night time is completely different. You don't have a shear production. Only the shear production happen in the base of the mixed layer, because the shear get trapped and thermocline is always stable. Now, yeah, it matters a lot, because this convection is actually dictate the top surface. Okay, so when you say dictate the top surface, if you don't have this mechanism like evaporation or the top surface will not get control. Say for sea surface salinity, without evaporation, sea surface salinity is not going to change. But now you have evaporation, right? Because you have salinification. So it matches the observation. So now is poses a very big question and concern. Okay, really we need to resolve these scales? Yes, if you don't resolve the scales or you don't include the mechanism of the scale, we get the biases, and that's why we get the bias of freshwater bias. So this is the one of the things. It is also surprising, before you running the simulation, we thought about evaporation is not playing any role, but now feel like the evaporation is controls the salinity. Same concept, if you don't have a cooling, the temperature will not be going to change. So the thermal convection and salinity convection both is important of driving the surface properties. So we also look at the storm induced mixture, because ocean is always have something like the fast moving wind. Okay, of course when you call as a category 4 and 5, then we call as a cyclone, but most of the time there is always a cyclone. It might be category 1 or less than 1, but there is always like the storm present in the ocean depending on its magnitude. We also able to using this type of system, we can resolve this type of mixed layer. And there also we have seen the impact of both the buoyancy forcing and wind forcing together. Okay, the figures are very similar, but here it happens over 8 days or 10 days time, because during the storm period you also excite inertia waves. Okay, which is also talked about in Mani's talk. Okay, now this is the one I like to finish, and then we finish the talk, and then we'll come back tomorrow again. Now, convective mixing. Okay, we talked about this salinity driven mixing is control the sea surface salinity. Now we try to understand again the sea surface temperature, how the sea surface temperature get controlled. Okay, so one of the controlling thing we understand, say for this we choose this particular phenomena of thermal, what is called wind induced mixing, and here we can run the system only buoyancy forcing, because during the fast moving wind you have a huge evaporation, right, and the evaporative cooling. So we can give the only cooling, and we can have only wind, or we can have a combined. And this is the 3 scenario. When you have only cooling, what will happen? The heat is coming from the top because you're cooling, so negative heat is going down, right? So this is the way is the heat transfer occur, right? So you're cooling the air part, cooling the upper layer, and those water parcel is coming down, and they change the property of the subsurface. Okay, now you have only wind, it has only shear, correct? It doesn't have any buoyancy forcing. So what will do? It will entrain, it only can change the temperature by entrainment. Okay, so heat flux is always has to be from the top to bottom. Okay, so it's a different direction of the heat transfer, because top surface is always warm, so and bottom is always cold. Heat transfer is this way because it's entraining, and convection is the opposite way of heat transfer. And when you both are present, you can see. But interestingly, when you have only wind forcing, the entrainment is not enough to change the soft surface. Okay, so the top surface never changes even you only have a wind. So the convection or cooling is very important, changing the subsurface and the SST. So you see that even these small scales are playing a very important role of dictating the upper surface. That's it. We'll come back tomorrow about more small scale and how they're connecting the large scale. Thank you.
Thank you so much for this great lecture. So unfortunately, in the interest of time, we won't be able to take any questions, but feel free to talk to Bishakhdatta in person, and we'll meet back at 11:45. Okay, thank you.